In this tutorial, we'll be creating this tree using L systems. I'm going to show you how you can hopefully implement it in any programming language, any graphics library. I'm going to tell you your maths of it, and hopefully you'll be able to interpret that maths and that pseudocode into your own language quite simply. L systems aren't difficult. In 2D, it's very easy, and so you should have no problem implementing this. If you do have problems, the code will be available on GitHub where you can look and analyze it. You can also create any issues if you find any problems within the code. So let's begin. I'm going to program this in the Go programming language. It's a language I like, but because I'm going to explain it in a sort of pseudocode way, you should be able to implement it in any language. You'll just have to change the syntax. The code will be available on GitHub. I'll also be using later on as a visual representation raylib, but that will be later on. So I'm going to make my file. I'm going to begin straight away. I'm going to make my main.go package main and just set up the main function. It's got my parentheses. So if we go back, the NL system is a string, and so we need an axiom to start it, the number of iterations it goes through, and then there needs to be a set of rules, and when it goes through it, it changes the string, and eventually we'll output with this long set of string. The more iterations, the exponentially increases the size of string in a Fibonacci way. So I think a good start would be create L system, which will be like the main function, and this will contain like the iterations number we want. That'll be an int. The axiom would just be a string. If you don't know Golang, you have to declare the data type when you put it in. If you're on Python, you don't have to do that. So I won't be going through too much detail. So I've just zoomed in so you can see a bit better. For what we have our function, and what we want is a start string. So in this case, I'll do a variable like this, and it'll just equal the axiom for now. And we're going to manipulate the start string as we go on. And then we'll need the end string because this will be our output. So this will obviously, at the moment, it'll equal type nothing, just an empty string. And then for I equals 0, and I is less than the iterations, we will increment. So we have our start string, which will equal our axiom because that's the starting point, and we'll end up with an end string, which will be our output. And then we're going to loop through the iterations. And so our end string will need to equal a function to it, so our process string. And within this, it will contain its start string. And eventually this start string will equal the end string. And actually, we don't want to return the end string as our output. So we go through, the end string will equal our new outputted string from the start string. And then we'll also edit the start string of the end string. So we go through, we have our start string, this is what it's going to start off with, and then we'll end up with that. And then because we have more than one iterations, we'll also update the start string. And so on the final iteration, we'll end up like that. Next we need our process string. Needed to find it's a function. And this will contain our start string. This would be a string type. So the process string will go through each character of our string, and it's going to send that character to a new function, and that function is going to check the rules, see if it matches with any of the rules that we have listed, and then return the new string with the updated and overwrite it, and then we'll return that new string back to the old string. So we should end up this much longer different string if the rules match. So to do that, it's quite simple. It's quite similar to our last function, which is we just need to loop through our string. So new string, which is going to be our output, it's going to be equal nothing. And then we want to for loop through. If I have for loop, I'm going to get a character, and this will equal the old string, which in this case is our start string. So I'm going to update this name. I think it makes way more sense than this. Like that. And then our new string will equal our new function, which will apply the rules like this. And it, oh, string. Oh, we'll pass it through as a character, as a string, because this is considered a rune in Golang, so it can be a bit messy to work with. And then we return the string. If you want to know what this underscore is, underscore in most languages means you ignore that variable. So in the case of just Go, this is Golang, fairly specific. When you go through a range, it will give you the individual element. So this is a case our character, and also give you the index of the number, like the essentially the I, so the iterations. But we don't need that, so I've underlined it, so I'm not using it. Just a heads up if you didn't know what that was. So I also noticed something wrong in process string. First of all, not a new variable, but also we're adding the string together because we don't want to overwrite it. We want to keep adding to it. So we make the new string, and then we add it the previous one. So we get that exponential Fibonacci sequence. So otherwise, we'll just get an overwritten string, and we won't have any progress. So I forgot with Golang specific, we need to declare what we are returning. It is a string, and we need to do this one as well. This is just Golang specific. I thought I'd just show you the change before we go further. We don't need the parentheses, so there you go. So our next step is to do the apply rules function, which is where we pass through our character and check if it matches any of the rules. If it does, return the new string with the new rules. If not, then just return the previous, return it itself. It doesn't need to be changed. Really simple. So function, apply rules, and we're going to pass through our char, which will make it a string in this case. Like we said before, I don't want to personally deal with runes and Golang. And again, we set up our new string that equals officially nothing. And then if the character equals, for example, we'll do the example that's seen on Wikipedia, which is like A, B, and A, B, B, B. Hold up, if you've seen it. There's A, and I've also done this wrong, so like that. And then all we do is we set the new string to that value. So we can set it to AB. And then we can do other ones, else if jar equals B. And I'm also doing like Python. I don't mean to do it like Python. I don't want colons, we want these. There we go. And then we can tell it and string. And why does that say? I'll do that later. As AA or something. Anything really. And then else, it will just new string will just be the character. It remains unchanged. And then we these goddamn spelling mistakes. And then we can return it string. And we need to tell Golang that we want to return a string. And my time's over. There we go. No bugs. That's it. As this is probably not the best way to do it. You can use if statements, you can use switch statements, and you probably obviously don't want to, depending on your application, you don't want to hard code it. You don't want, otherwise you have many ifs and else. You want to Well, ideally have an array of items and then loop through and then check if it matches and then return the correct one. So there's different ways of doing this. For this sake, I'm just doing if else because it's kind of an easy representation. If this equals that, then you return that essentially. That's why I'm just doing it like this. But there is obviously way more optimized ways. You don't really want to hard code it, otherwise it's really hard to change. If you want to build a natural system, you probably want it so you pass in the rules as change it up to make it different. Now then, what next? Well, actually, that's it. We can now tell in our main function to call our create else system. So in this case, I'm just going to do print line. I'm going to tell it create else system. I want it to be 5 iterations, and my axiom is just going to be A, which is what which will match all the rules. If we put it something else, it won't. And hopefully, if we run it, go run main go, there we go. We've ended up with a string of different characters. I'm just going to look in A B A B B, random. Kind of nonsense at the moment because they don't mean anything. But this is essentially an else system. Obviously, it's just a bit random. It's just random characters that aren't doing anything. And what we really need to do next is provide a visual representation. So now I'm going to show you how you display this 3D and 2D. Now this is all great and everything, but how do I represent this in a visual format? How can I see my results as a tree or a plant or even a building, as some cases have been used? Well, I'm going to show you now, and I'm going to be using raylib. Raylib's just a graphics library mainly for game development. You can try and use everything, but I'm just going to try and explain it in pseudocode as simply as possible, mainly explaining the x and y coordinates, where something should go. However you render it is going to be different. Obviously, this case could be raylib. It's a lot harder to kind of be concise with visual graphics, but that's how we're going to do it. So I've just quickly gone through and set up the kind of boring stuff. So I've installed the raylib package, done all the Go mod stuff, and I've set up like the render, the update. This will all be on the GitHub for you to copy, or you can implement it yourself. I just thought I wouldn't show this because it's very unrelated to the whole level system tutorial. So to draw the L system, to render it our screen, we're going to get a function that goes through our output, our L system string, and it's going to go through each character and say, is this a rule and what it should do. So essentially it's the same as the apply rules, except we're now going to tell it what to render rather than replace string. So we're going to make a function, draw L system, and this is going to have our instructions, which will be our string. And what we will need is obviously the x and the y position. So I'm just call them pos x equals 0, pos y equals 0, the distance, which will equal 20 in this case. So that'll be 20 pixels. And what we do is for character equals range of our instructions. And I'm going to change this to a command, which is going to just convert this rune to a string, just because it's easier to deal with. And if cmd, the command, equals f in this case, I've also, in the apply rules, change it to f rather than a and b, because it's based on total graphics, so this is how you should ideally do it. Makes more sense as well, f for forward. And then we'll tell it to render, in this case, a line. So draw line ex, which contains start position vector, 2D vector, and the end position vector, the thickness of that, and the color. So our starting position is quite easy. It's going to be just our current position x and our current position y. So vector 2 add, and it will contain position x and position y. Next we need our end position, so this is where it will draw it to, and that will be again a vector 2. This is just for more Golang case because this is how it wants it. And again, we want x and y. But so the end position is, I'm going to declare it previously because we need it. So the end, I'm going to make one a variable called the end position x. And this will equal our position x, but we add on nothing, the x for now. We will later. Our current position and our current position y. We plus y plus the distance. Now I've just left the x as it is because we're not rotating any angles yet, so we don't need to, we're just going up in a straight line, so we don't need to tell it to go right or move the x. So the x will just remain the same for the moment, but it obviously will change. At the end position x, and y is the end position y, and we'll just set the thickness to 5, and we'll set the color just to red. Now, we're not done yet. We need to tell, we haven't updated the position x, so our position x equals our end position x. That's, we update it. This will equal our end pos y, because that is now our new position. That also, when we go back and we look through, when you find another f, the position x is now going to be what it last was, so it will actually progress further. Now, I'm actually going to make a global variable and call it output. And this will equal a blank string, and this is just so I can initialize the L system, so draw, rather than get it running the L system every frame. I can initialize it, so you only create it once. In this case, 5. Then I should pass through f as a string. I've done it the wrong way around. Yeah, so when I run an application, it's only going to run that once, but when it comes to my rendering, I can do it. Don't need that. Draw L system. Let me just pass it the output. So now when we run it, hopefully when we run it, I've boobed up somewhere. Oh, I think I was right, actually, of this. It was the height, but in this case, so technically we're subtracting from the distance because the height is actually the bottom part. Is the way raylib handles it is that 0, 0 is the top left of the window, so we actually want to render it, so we want to take away from it. Oh, there we go. Okay, now going. I was trying to set up cameras so I could do it at 0, 0, but it wasn't working. So in this case, it's really 0, 0, so we're just taking away, and that's a plus or something. Yeah, there we go. You see, it's drawn a nice, lovely straight line. Excellent. Okay, so this is where things start to get a little bit tricky. So the next is the angle, and to us in our minds, it's quite easy. Oh, if we want to go 20 degrees, oh, it's just 20 degrees. We have to somehow convert the angle to an x and y position on our visual representation. Now, if you've used any other L system frameworks, they will already have this covered for you. So it's not too bad, but if we're, in this case, because we're coding it from essentially scratch, except for the graphics library, we need to figure out where the x and y is. But before we get that, let's add our rule into our case. So we need an angle, which is the current position, so the angle will equal, actually, it's going to equal 90, so 90 degrees, and this will come important later on when we come to figuring out why we need that, and I'll also show what happens if we don't do that. And we need also have a command that equals an angle, so in documentation in the official book, The Algorithmic Beauty of Plants, it's a plus, which tells us that we should increase the angle, and you tell it in the draw L system, we should actually pass through what angle we want to increment this by. And so we're going to add a new parameter, and this is going to be, I guess I just said the normal int. It might have to change to a float or something. And then we add on, I shouldn't actually, I'm going to name it vertical angle for now. And then we can pass through the degrees of the angle. So then we just add on to it. So we're adding onto our angle. in this case, whatever we set that value is, it will increase it. And then for our second command, this will equal a minus. And that decreases the hour angle. So our vertical angle will be subtracted by that amount. So, nice. So, we have our angle. How do we interpret this angle as an x and y? So, what we actually have, what is the x and y? The x and y is what's called the Cartesian coordinates. If any of you done maths in like GCSE or high school or whatever and did trigonometry, will know there's another type of coordinate system which is called the polar coordinates. And the polar coordinates is the radians, in the sense of a circle, and the degree. So with the degree and the radians, you can find out where the x and y is. So you can convert polar to Cartesians. It's very useful in this case. And it's actually quite easy. Most programming languages come with the required functions, the math functions. So in this case, the cosine and sine, and pi as well. So let's do it. So I'm going to call this function polar underscore to Cartesian. And what we need is the radians, which is technically in our case just a distance. So 20 radians technically will be our first. Actually, it's in 32. You might have to change that because it might be require float, but we'll get to that. We need the angle, vertical angle in this case, which is an int 32, or not an int 32, an int. And we need to return both of these values, which I believe there will need to be float 32s. So both floats. So add x or y. We need to actually convert our angle, our angle into the theta or the phi. I can't remember which one it's called. I'm just gonna call it theta for now. And the theta vertical, and this will equal the vertical angle times the pi, and then divided by the degree, the flat plane degree of 180. Now it's saying it's imported it. Why is it red then? Oh no, it's just IntelliSense being weird. So this is one way of doing it in a language, but there's also another way, which is, I believe it has it, math.radians, and we can just pass in the vertical angle. It actually just works exactly the same. If I hover over it, it might even tell me. Are we sure it's not a capital one? Or whatever. There's some depending on your language, like Python has this as well, where you can just directly convert. You can do math.radians and just put the angle in. I'm just going to go back to the original way, which is the vertical angle times math pi divided by 180. Now, how do you find it in a 2D? The x should equal. Well, to find the x, sorry, let's make it more clear, is that we need the radian, so our distance times math.co, or the cosine in this case, and we need to pass it the theta vertical, and that's our x. So that's how we find our x coordinates, and then our y coordinates is similar, but instead we do the sine instead, rather than not just the cosine. And this is again just the angle, and that's actually it. That's all we get. That's all we needed to find the x and y position. It's not that hard looking at it, because obviously they provide us with it, and if you put it in the calculator, you just use the cosine function into it, and the radians. This is how we do it in programming, in a programming language. And I'm also going to just space these out evenly. And all we need to do is return x and y. And that should be it. So I'm just going to further explain the polar to Cartesian coordinates. I'm just going to draw it out for you. So let's say we have our grids, our x and our y. This is our y, this is our x, this is positive and this is negative. Top is positive and this is negative. If we have our degrees and our length, we need to figure out where that plots on y and x. And we've got to imagine that at the center of this is our 0 in the center of our point. And then we get 1, 2, 3, 1, 2, 3. So we go up 1, 2, 3, y, 3x. And in our case, for a radian, it's like a circle. Let me actually draw a circle. It might look better. This. Around about that. We have like 3 radians. And so we know if our polar coordinates was like 3 radians and a degree of 45 or something, and we know that our x and y point are somewhere in the third circle. That's how far we want to go out. And so we would need to find where this is plotted on an angle. Now, it actually goes from the radius actually goes from 360 all the way to minus 360, and this is why in our we set the vertical angle, this angle, automatically to 90 degrees because we know that this will cause the tree to grow upright this direction. If we would leave it at 0, it would be point at this nothing, and would sometimes in some programming languages it will error because when you try and do the calculations, you're trying to divide by 0 or whatnot, so it won't like it. And if you just do it by 0, it will try and go this way instead. So that's why. So to find the x and y with this, the equation is for the x, that's not the x, it equals the radius, which in case is 3, and then the cosine with the degrees, so cosine 45 degrees. And the y equals, again, the radius, this time it's the sine. Sorry for my terrible handwriting. And then the degree, which is 45. And these both equal, in this case, around about 2.12. Obviously, depending on the angle as well, it will also give you a negative value. So it will also support that. Excellent. So for our case, the center of our thing is where our last position x and position y was for our L system. So where current position is. And then when you do this calculation, and we either add or subtract the value to the x and the y, and this will then position it in the correct direction and rotation to make it look clean. So now we need to return our x and y that we've converted from our angle to our draw system. So in this case, we can tell, and we just tell it. First, let me clear these errors up that are happening down here, which is the fact that it's wanting a float 32. So I'm just going to convert these to a float 32. It's also complaining that this is not a float 32. Oh, it's asking for float 64. I might as well just convert this to a float 64 just to make things a bit easier. So again, in our thing, when you want to tell it our end position x and our end position y equals our polar to Cartesian, and we give it our distance, which is 20, and our vertical angle, which will convert to the float 64. And we also don't need to declare these as new variables anymore. It's also going to get angry because it keeps saying that these are the wrong data types. And make sure your data types are all correct. I keep just converting them on the fly, which is annoying. This is also because they're all asking for different types, which is a bit frustrating, especially with raylib as well. Raylib's asking for floats and all sorts. Now the end position x is actually just the position x. In this case, I'm going to make a new variable and call these the end x and the end y. Not the best naming, but it's going to be the position x plus this, and then this, take away this. Again, it's, you know what? To fix these annoying telling it it's not a float 32, I'm just going to make sure they're a float 32 from the start. I'm just going to do this. Distance is not used. It is used. It's not used because it should be here. There you go. And then not used. And we can get rid. Now we can get this plus x. In fact, this needs to be end x now because end position is over. Nice. And then I believe this should be minus or plus in your case, depending. And now we can add these in. God damn. Doing that. It's not. I've accidentally deleted something from here. Return new string. There you go. Now we need a new else. In this case, a new rule, I should say. If char equals. Well, actually, no, we don't need that. Actually, sorry. We could do, but I'm just going to add a plus in this. And then a minus, so it will go back to its last position. Hopefully, when we run this, it should all be at. We have not enough arguments to call draw else system. Aha, of course. The distance. The angle, sorry. 20 degrees is going to be my angle. There we go. As you can see, it's gone in a big fat circle. Let me add this minus back. I just removed it off camera quickly. This negative. So hopefully it should do like a zigzag. There you go. So there you go. You see it's now perfectly sort of following it. Yeah, so there's our angles done, which is nice. So to clarify, just to clarify why it wasn't working before is because a float value, a float data type accepts decimal points and an int doesn't. So what it was essentially doing, it was just like rounding out, and so this basically set it was making no change. It was setting the x and y to 0 or nothing. So yeah, make sure your data types are correct. Otherwise, you will get stuff like that. So that's just something I thought I'd inform why that didn't work. So if you've ever looked at else systems in some of the manuals or even in the book again, there's something called the stack, and the stack is essentially where it's represented as a square bracket, and essentially we store everything onto the stack, and then of the position we're currently on, and then when we add onto it, we do some, let's say, do a bit of movement, do a bit of angles. We then close the stack. It will return back to its previous position where it first set. This is actually really easy to implement. Essentially, we just need an array, and when the stack is called, we just append to the array, and when the stack ends, we just pop the last item. So we can also do embedded stack. So we have to make sure that we remove the last item that was used. So when the square bracket starts, you could do another square bracket within that, start another stack, and when you close that stack, it will close the last item in the array. So when we append array, it appends it to the end of the array, so that becomes the last item. So when we want to pop it, we remove that last item, just in case you have an embedded stack, which is not impossible. Okay, first, let's just add that into our draw else system. Else if cmd equals the square bracket, and I'm just going to set it up as else if the cmd equals that, which is to pop it. So we're going to need an array. Now, I'm going to call it the stack, and it's going to equal, and it's going to be a multi-dimensional array, so we can store more than one array within it. So essentially, our array is our containing items, and that's going to go into array. And so when it comes to removing the stack, popping the stack, we just pop the last array. If we just have a single array, then it'd be really hard to add more than one stack to it, and obviously we'd have to go through and delete each one. So this is how we're doing it. Now the way Golang handles arrays is quite finicky. So in this case, this is just an empty array, multi-dimensional. So each square bracket represents an array. So this is 2 arrays, and unlike Python, where Python is really easy to make a multi-dimensional array, and Golang is a bit different. So we want an array, and when this command is called, we want to add to it. So we're going to append to it. Append stack the one we want. So this will just set it to the last one, and this needs to contain our float 32 array. And what we have stored already, we need every bit of detail of the location. So the x, the y, and the angle, and the distance, I guess, as well. Even though the distance depends if you change the distance midway through, but mainly just the x and the y, and the angle. Just in our case, but this can essentially go as much information as you want the position, depending on how expansive your else system is. So we just need to add our position x, our position y, and our vertical angle. I don't need to be a W, just like that. It's just, why is it? I'm just double checking why it's gone yellow. Let's ignore that for now. Because I've got let's just pretend. Let's just yeah. Anyway, so stack. So the popper stack, we need to firstly get the information out and load and override our variables so they equal the previous values we had. Popped, and so I'm going to call this popped. Let's do capital as well. I'm going to also change that stack to a capital for consistency. Popped, and this is going to have our last element in our array, so that we want to get the length stack, and then -1. Otherwise, we'll get an override because it would try and call. It counts. I believe it counts from 1, so this is why it does this. Oh, it also needs to be square brackets, not parentheses. Nice. And then our posx will equal the first element, wherever our position x was, which was the 0th element, it's the first element, position y, which equals the first element, and then our vertical angle, which equals our popped popped our second element in our array. And then now we just need to tell the stack that we want to pop it. So the way it's done is simply stack. This is like this is why arrays quite interesting. In Golang they're not the same, but to remove the last element in our array, we do that. And there we go. So that gets the length, and then we take away 1. Yeah. So if you're in a different language, it's probably a lot easier. So I'm going to update my apply rules, and then this is going to now include the square brackets, and we should actually get a tree-looking product like out of this. I'm going to. There are examples within the books and online that you can use. So this is an example I found from a website, and I have that website linked in below. So here's f equals ff, and else another rule, quite simple one, but and this is x. If char equals x, so in this case, it has a string, a character that won't affect the output, but is in fact a rule. So you can see this as well. X is quite a common one for an axiom starting point, and this will equal f square bracket, so a stack, rotate with a plus, end that stack, and f in between that, and then negative, so it goes back an angle, and then close that bracket, and then plus, take a right, and x, and that's it. And we also make sure to update your axiom, so we need an x to start this one. The next, we'll keep this going. I'm going to have 5. Hopefully, fingers crossed, when we run this, we should have a tree. We do. It's just really big. So let's decrease the size of that distance to, let's say, 10. There we go. Now, quite something's not right here. Okay, so I figured out why it didn't work, and that was because where these were f, it should have been x. So now when we run it, there's our tree. Perfect. I do hope you enjoyed part 1. Please do subscribe if you want more information and more tutorials relating to mathematics in computer science, especially and game development, and other aspects like photorealism and ray tracing, which I also like to dabble on. Anyway, good programming and have fun.